So why is that meme really funny about, not having to parameterize your line integral if your vector field is conservative? Because then you just evaluate your potential function between the starting and stopping points. And that's the point. I'm going to prove the theorem right now, which is really kind of cool. It's an easy theorem for you to understand, especially in light of the fact that you know what the fundamental theorem of calculus is, as well as the chain rule. So both of those theorems are required in order to understand the proof of the fundamental theorem of line integrals, which is kind of cool. So here's the proof. It's pretty quick. We're going to assume that the curve C is a smooth curve, and smooth just means there's no sharp corners or cusps or anything like that, so that the velocity vector isn't equal to 0, or it's not undefined. Okay, now because the vector field is conservative, because that's part of the premise of this theorem, that means that he's somebody's gradient. And that's the beauty of knowing that your vector field is conservative. So what does that mean? It has a potential function. And the potential function is that scalar function f. Briggs sometimes uses a Greek letter phi to denote a potential function. You probably noticed that when you were taking your My Math Lab quiz, whatever it is here. So, and your vector field here is the gradient of the potential function, which means, since you guys already know about gradients, because you've been with me now for almost 4 months. Oops, that's supposed to be, these are the partials that are the components of your vector field. Okay, so we know that. So then it follows that the line integral that we're trying to figure out, and it's one of these vector line integrals, FDR, dot product there, is going to be the regular single integral evaluated between the limits of a and b, f dot product with the velocity vector dr dt. But that's going to look like, this gradient. I'm going to abbreviate so it's not so bulky with the notation, fx, fy, those partials. And then we've got the components of the velocity vector there. And once we take the dot product, which we'll do in the next step here, you're going to have this first partial of f with respect to x times dx dt plus the first partial of f with respect to y times dy dt. Okay, fine. So what? We all know how to do that. So what's the big deal? Well, what I want your eyeballs to focus on, because this is the really cool step, is this stuff that's in brackets. Does that remind you of anything? I'll give you a hint. I'm going to do one of those schematics from a couple chapters ago.
Chain rule?
Mm-hmm. Do you remember this? Where you have fx multiplied by, dx dt plus fy times dy dt. So you remember the chain rule?
Yes.
Awesome.
So this is the chain rule. So wow, that's really kind of cool. So if I replace all that junk in brackets with what it's representing the derivative of the original function here with respect to time. So it's basically, that is, I'm using the chain rule backwards now, it's ddt of the function. So that's the chain rule in action. So I'm using the chain rule kind of backwards to get that. And then what? Well, now you're going to use the fundamental theorem of calculus, part 2, which basically says that integration and differentiation are basically are reverse operations. They undo each other. So we're taking an integral here of a derivative. What do you know about taking the integral of a derivative? What's the answer going to be?
The original function.
The original function, yeah. So it's going to be f xy evaluated when time goes from a to time going to b. And that's essentially going to be f evaluated at this point, x of b, y of b, which is the ending point of the path minus the function evaluated x of a, y of a, which is the starting position. And that's it. So end of proof. And that is the fundamental theorem of calculus getting involved to finish this proof out, which is pretty cool. So if you understood that proof, and it's not that hard because of everything that we've done this semester, congratulations. Pretty cool, huh? I don't do a whole lot of proofs in this class, but for you math majors, you want to know about how to do your proofs. Okay, so we did an example last time before I finished class in the last few seconds. Here was an example where they asked us to do a line integral given a vector field, and it turns out that the vector field was indeed conservative, which is awesome, because that means that when they gave us the starting and stopping point of the curve, we don't have to do any parameterizing of this curve to do the line integral. Great. So then what? We use the fundamental theorem of line integrals instead. So you get your potential function by integrating m with respect to x. Don't forget your plus g of y here. And then you integrate n with respect to y. And then your plus f of x. And there, in this case, there were some duplicates. Please do not add those together. Just take one instance of it and then come up with your potential function here. And then you evaluate that potential function between the beginning point and the ending point. Okay. And we got a 4. And we'll do more of that today. Don't worry, it's coming. We'll do some more examples with the fundamental theorem. But new topic, let's talk about independence of path, which has everything to do with conservative vector fields and the fundamental theorem of line integrals. So this is all related. So what of this topic, independence of path? Well, from the fundamental theorem of line integrals, which we just proved, if you've got a vector field that's continuous and it's conservative on some open region R, then the value of this line integral will be the same for every piecewise smooth curve from one fixed point to another fixed point, as long as those fixed points don't move. So we say that the value of the line integral is independent of path because it doesn't care. So a little picture of what I mean by this is, let's say you had some region here R, and here's the starting point A, and here's the ending point B. Let's say somebody said, oh, well, I need you to figure out the line integral on this path. Woo! Call it C1. And then figure out another line integral going between A and B, but on a different path. How about this one goes, loopy-loop or whatever it does, and maybe it goes all the way around the island, and then it ends up at B finally. It still has the same starting and stopping point, but it went a very circuitous route.
Maybe this is a mountain.
What's that, Dominic?
Maybe it's a mountain, like a hiking trail.
Yeah, it's a long hiking trail. Like, yeah, the pink one is like, woo, go all the way around and go nuts, and then finally end up at your destination. So which of those line integrals is bigger than the other? Well, the answer is neither. They're going to have the exact same value. Well, wait a minute. Shouldn't the long hiking trail line integral have a bigger value? No. Because we have independence of path. Because if you have a conservative, this only works for conservative vector fields, okay? If you did this with the vector field being non-conservative, oh yeah, there'd be different values for those two line integrals for sure. But if it's a conservative vector field, no, independent of path, baby. We don't care. Okay, let's do a couple of definitions that will get us to the theorem. Okay. Well, one definition. Okay, so you have a definition of what does it mean to be a connected region, connected. And I have two little diagrams over here. This first diagram here, R is connected, and then over here, R2 is not connected. Well, what's the difference? Well, the second region has two islands to it. You can think of two islands. And in order to get from A to B, you have to leave the island and kind of splash yourself in the ocean a little bit in order to get to the finishing point. So you have to leave the region. So it's not a connected region. So you can think of Hawaii as being not a connected region because you have to jump off the island into the ocean to get to the next part of the region. But here, this is a connected region. Okay, so what the heck? Why do you need connection? So you need to have 2 points in the region that can be joined by a piecewise smooth curve that lies entirely within the region. Okay, because you need it, otherwise this theorem won't work. So this theorem, which is the independence of path and conservative vector field theorem, says the following. If F, that's your vector field, is continuous on an open connected region, then the line integral FDR is independent of path. Okay, and then it's an if and only if statement. So hold on a minute. Then the line integral, and this is one of those vector line integrals, and it will work for FDR or differential form, since those are really the same. This is the other one, somebody already did the dot product for you, is independent of path, IFF. Does anybody know what IFF means? It's short for something.
If and only
If and only if.
If and only if, yeah. In mathematics, they use a lot of if and only if statements. So it stands for if and only if. The vector field F is conservative. Now, folks, an IFF statement is very different from a regular if statement. Very different. Why? Because it's what I call a double header statement. And you put a double header arrow on there. That's another way that mathematicians denote if and only if statements, because you can read it in both directions and it's still true. And not all statements have that. Like it's a regular if statement, you can only read it in the forwards direction only for it to be valid. You can't read it backwards and have it still be true. But an if and only if statement, you can. So I'm going to read this forwards and backwards. So the forwards direction, this direction is the line integral is independent of path if the vector field is conservative. Now, if I read it in the reverse direction, F is conservative if the line integral is independent of path, and that's still true. So either way you read this, it's still going to be true. That's kind of nice, if and only if statement. So that's what the theorem says, and it's a very, very important theorem for you to know in this section. Okay, so let's do.
Professor.
Yeah.
Professor. Okay. Row 2, column 1 of the box. What is the wording between if and of?
If and well, there's only one if there. I'll read it to you and let's try it. I'll start from the top and hopefully that will answer your question.
Okay.
If F is continuous on an open connected region,
Okay, region.
Then the line integral, which looks like FDR here, is independent of path if and only if the vector field F is conservative. Does that help?
Yeah.
Okay. Let's do some examples that require this theorem. Okay, example 4, check this out. I'm going to ask you a question now, so you answer me in the chat box or whatever. Wake up. Here's your sign, Vanessa. Woohoo! Wake up, people. So here's a vector field. Yeah, so what? Prove that this line integral is independent of path. And then use that fact to evaluate this line integral, FDR. And this notation where you have a line integral and instead of a C underneath the line integral, you have the starting and stopping points attached to the line integral symbol. That's very standard form. It means that they're giving you the starting and ending points of the path for a line integral. Cool. So folks, how are you going to prove that the line integral is independent of path? What do you think that needs to be done?
Conservative test.
Show the vector field is conservative. That's all you need to do to show that the line integral is independent of path. And that's enough by the theorem. So that's kind of cool. So by the theorem, if we show that F is conservative, we will have shown that the line integral is independent of path. That doesn't mean we've evaluated the line integral yet. We still have to do that, part of the problem. But we will have shown that it's independent of path, that it doesn't care about, you know, how it got from the starting point to the stopping point, as long as we have the starting and stopping point and we have it on a smooth connected region. Okay, so so what do I do? Well, here's the M component and here's the N component of the vector field. So how do we show it's conservative?
dm dy.
Yeah, dm dy is equal to dn dx. And that will be enough to show the line integral is independent of path. Okay, fine. Let's hit it. So here's m. It's 2x plus y cubed. What is the derivative of 2x plus y cubed with respect to y?
3y squared.
Mm-hmm. And then is that the same as dn dx? So somebody besides George, here's n, 3xy squared plus 4. What's the derivative of 3xy squared plus 4 with respect to x?
3y squared.
Yeah. So you see that these are the same? So
Yes.
the vector field's conservative. That means the line integral is independent of path. That means the line integral doesn't care about the curve. It only cares about the starting and stopping points of the curve, independent of path. Okay, fine. Now, how do we actually evaluate the line integral? Well, no parameterization needed, which is awesome. Well, first of all, they didn't give us enough information to even parameterize because they just gave us the starting and stopping points, and they didn't tell us if it was a straight line segment or maybe it got from the starting and ending point along some curvy curve. We don't even have enough info. So we couldn't even do if we had to parameterize. But we don't care. So let's go get the potential function. And what I mean here is we're going to apply the fundamental theorem of line integrals in order to evaluate the line integral. That's what we're doing right now. And folks, this coming quiz, like this weekend, you got to know how to do the fundamental theorem of line integrals, like more than once on this week's quiz that's upcoming, okay? On midterm 4, I'm going to for sure put one problem on midterm 4. You got to use the fundamental theorem of line integrals. On the final exam, I'm just telling you in advance, so you know what to expect on the final. There will be a problem that requires the fundamental theorem of line integrals. Only one. Like if you're doing like, oh, wow, she put 2 or 3 of these fundamental theorem of line integrals on this final. Cool. You're doing it wrong. It's only going to be one of those. Okay. Okay. So you're going to go get m dx. And so you're going to integrate 2x plus y cubed with respect to x. Cool. Cool beans. So what's that going to be?
Hello.
Hello, I'm waiting for you. What do you think that the
Oh,
integral of
Oh.
help me out here.
X-
I know I'm doing a
X
lot of
squared-
talking.
X squared plus
okay, plus.
xy cubed.
I'll
or,
buy it. Plus,
uh,
not
of
plus
y.
C, plus something else. What?
Like a function of y.
Yeah, so how about h of y? Give me something, okay? All right, now how about n? You're going to integrate that guy, which is 3xy squared plus 4, but integrate him with respect to y, okay? Somebody besides George, help me out. George, I know you know this. You're fine.
xy cubed plus 4y plus h of x.
Okay, excellent. That sounds good. So xy cubed plus 4y plus say f of x. Very good. And I like to draw a line and add them together to get, acting kind of like I'm adding them together, but not quite. So I notice I've got a couple of duplicates like xy cubed and there's another xy cubed. Should I add them together?
Oh,
No, just take one of them. Okay, one of them. And then I've also got an x squared and a 4y. And now you could put plus c. Okay, now what? Well, this line integral that I want us to do here, we can actually do it now. So this line integral 0, 1 up to 2, 3 f dot product of dr. You don't even have to do any dot products, any parameterizations. You're just going to take the xy cubed plus x squared plus 4y. And you don't have to use the plus c when you're doing the fundamental theorem because it'll end up canceling anyway. So just don't even put it in there. And then you'll evaluate between the starting and stopping point. And remember, order matters. So always evaluate at the ending point first. So you're going to plug in the point 2, 3 into this potential function, 4 times 3, whatever that number is, we'll get that in a moment, minus, and then plug in the lower limit of 0, 1 And anytime we have a 0 for x, that's just going to be 0. So that's not very interesting. And then, oh, great. What do we get here? We get 27 times 2 is 54, plus 4, plus 12, minus 4. Okay, I think I get, doing all the arithmetic here, I get 66. Okay. No parameterization needed. Wasn't that great? So that just brings me back to the meme now that, you can really understand here. If you spend a half an hour trying to parameterize a curve for some obnoxious line integral, but then after all is said and done, what if the vector field was conservative? You just wasted a whole bunch of time. You didn't need to do that. Oh, well. Okay. I look long and hard for these memes, people. I hope you know. I like you to have a little bit of a smile, right?
I appreciate them.
So you got to have a little smile here. I know things are bad right now. Like, I think I told you that survey that a colleague of mine, not in the math department, but also a STEM teacher, asked his students about 4 weeks ago. Hey guys, informal survey. How many people would like just to take the final exam tomorrow and just be done with it? And more than half the class raised their hands. It's like, wow. A lot of people are just like, they want the semester to be done. But, and then he said, I hate to break it to you guys, we're not done. We're not going to take the final tomorrow. And they're like, okay. Letter B. The reason why I didn't give much space here is because there's not much to do. How do you prove that this line integral right here is not independent of path? In other words, it cares very much how it got from the starting point to the ending point.
A conservative test.
Yeah. So what we'll do is to show it's not independent of path, it'll be enough to show that F is not a conservative vector field. Okay, that'll be good enough. Well, what's F? They didn't give me the vector field straight out like they did the other problem. Like, in this letter A, they gave you, the vector field M and N right there. It's like, okay, there's my vector field's components. I'll figure out the,
Cherry pick.
You cherry pick. This is differential form. You're supposed to learn that already. So the M is the x squared y, and the N is what's multiplying with the dy, the 3xy squared. So what is dm dy, the partial of M with respect to y? What is the derivative of x squared y?
X squared.
Mm-hmm. So what about dn dx, the partial of 3xy squared with respect to x?
3y squared.
3y squared.
Yeah, are these two guys equal?
No.
No, not conservative. So that means that the line integral is not independent of path, okay? And it would care very much about the path. It's path dependent. Now, so here, knowing that, do we even have enough info to evaluate this particular line integral? If somebody said, well, screw it, evaluate it anyways.
I don't think so.
No, and the reason why is they didn't give us how it got from the starting to the ending point. If they had said, oh, it's a line segment, what is the curve connecting those two dots, then you could go, oh, okay, because you will have to parameterize. But if they didn't even give you enough information to parameterize, don't assume it's a straight shot. Don't go, oh, well, I'll just assume it's a line segment. No. If they don't tell you, you don't know. It could be some, here's the starting point, here's the ending point. The path could be some, weird circuitous route, and you don't have enough info to parameterize that weird circuitous route. So you can't even evaluate this line integral. You don't have enough info. If a person said, well, do it anyway, just tell them to take a hike. No way. Okay, I'm finally going to tell you how to determine if a three-dimensional vector field is conservative. I've been holding off. Briggs tells you a little bit earlier than I do, but I kind of hold off. I like to bring a little suspense into the situation. So you already know how to prove a two-dimensional vector field is conservative. How? I'm giving you a hint right now.
You just boxed it.
Yeah, just show me dm dy is equal to dn dx. Boom. You just showed me that a two-dimensional vector field is conservative. But I didn't show you how a three-dimensional one is. So let's get to it. It's not going to be pretty. Okay? So here's the test. Put stars by this because you're going to need this. You think you're going to need it on this Sunday's quiz? Oh, yeah. Think you're going to need it on midterm 4? Oh, yeah. Think you're going to need it for the final exam? Yeah. All three of those. Yes, 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 and yes. And it's not that hard because you already know one piece of it. So I just have to add a couple extra little factoids to help complete the test. So let's say you have a 3D vector field. So the components are labeled M, N, and P respectively. Briggs, I think, uses P, Q, and R, or F, G, and H. Who knows? Briggs is such a mess. Anyway, it's conservative if and only if. Hey, there's that IFF again. That means you can read this forwards and backwards, and it'll still make sense. So I hope you notice that this one you already know. So that you've seen that one already. Ooh, how do you know? Because that's what you have to show is true for a two-dimensional vector field to be conservative. So you only need to show two other things are true, two other equalities. dp dy is the same as dn dz, and dm dz is the same as dp dx. And boom, you got a conservative vector field on your hands. Now, if even one of those is not true, like let's say 2 out of the 3, like, hey, 2 out of 3 ain't bad. It should be conservative because, you know, majority rules. All 3 have to be equivalent. Otherwise, not a conservative vector field. Okay, so let's look at a definition now. And I love this definition. It's really important for both 2-dimensional and 3-dimensional, although I've only given the definition in 2-dimensional, 3D here. It's true for both 2D and 3D. So I want you to know that. So any expression where you have m dx plus n dy plus p dz is differential form. And so the 2D version, just so you know, would look like m dx plus n dy, because we don't have a third component. So you've already seen differential form, you know what it is, fine. A differential form is exact. Now that's the key word we're using here that's different. It's exact on an open simply connected domain D in space, if and only if, ooh, there's that IFF again. Ooh, double header, baby. Read it forwards and backwards. If and only if what? Oh boy, I just went back. I don't know where I am. It turns out, if and only if, stop, the vector field is conservative. So you already know what that means. For a 2D vector field, it's just, oh, dm dy is equal to dn dx. For a 3D vector field, you need all 3 of these equations to be true. Okay? So exact differential form. For those of you that have already taken differential equations, or maybe you're currently enrolled in a differential equations class this semester, hey, congratulations. You've probably heard of what an exact differential equation is, haven't you? Anybody in the room taking DE right now, Math 253? Yes, no? Yes, Chris is. Okay. You've heard of an exact DE, right, Chris? Yeah. Okay. So an exact DE for differential equations, folks, and they only do the 2D version, is if you have dm dy equaling dn dx. That's exact. And so good news, if you haven't taken differential equations yet, if you plan on it, this class will help you a little bit. Not a whole lot, but a little bit. Okay. If anything, by beefing up your integration and skills as well as your derivative skills, it will help you there. Okay, let's take some of those definitions and put them to good use. Okay, check out example 5 here. We got a 3D vector field. Oh, holy guacamole. Check it out. We got 3 components there. We're going to prove that this line integral is independent of path. How do we do that?
You gotta take the partials and set them equal to each other.
Yeah, that's gonna all we have to do is show that f is conservative to show it's independent of path. Doesn't care about anything about the curve, as long as you're given starting and stopping points. That's all you care about of any path. Okay, so we're going to show that, and then we're going to we're going to evaluate this line integral, and we're going to evaluate it using the fundamental theorem of
Fundamental.
line integral.
Mhm.
Yes, indeedy. And it's such a powerful theorem. Love it. Because you don't have to do any parameterizing. It's awesome. Okay, so let's show that the vector field is conservative. There's the M, there's the N, and there's the P. Let's do the equation that we already know and love. Let's see if dm dy is in fact equal to dn dx. Check it out. So the derivative of y squared cosine x with respect to y, I believe, is 2y cosine x. Is that going to give me the same thing as dn dx? Well, the derivative of 2y sine x with respect to x is 2y cosine x. Oh my God, they're the same. So far, so good. Okay, now let's see if dp dx is really going to give me the same thing as dm dz. Let's check it out. So there's p. What is the derivative of 2y e to the 2z with respect to x?
0.
0. Is that the same as dm dz? So m, what is the partial of y squared cosine x with respect to z?
0.
0 also, because there's no z's in there. Hey, 2 out of 3. 2 out of 3. All right, we got one more. Is dp dy really giving us the same thing as dn dz? Okay, check it out. P, what is the partial of 2y e to the 2z power with respect to y?
2e to do 2e to the 2z.
Thanks, Anthony. Perfect. And is that the same as dn dz? So what's the partial of 2y sine x plus e to the 2z power with respect to z?
Same thing.
Same thing. Oh my God, we have a conservative vector field because all three of these are equal. So yeah, so therefore f is conservative, and also since that theorem, that means that this line integral is independent of path. Doesn't care about the path. It only cares about the starting and stopping points of the curve. Fine. So we just did part 1 of this example. Now it's time to actually evaluate that line integral. Oh, well, you got to go get the potential function first, because that's what the fundamental theorem of line integrals says. Go get that potential function, the scalar function, and evaluate it between the starting and stopping points, which are hooked on right to that integral symbol. Okay, so go get the potential function, which is a function of 3 variables, since this is a 3D vector field, f, x, y, z. Now, Briggs might call it phi, use the Greek letter phi of x, y, z instead. Either way, whatever notation you kind of have to get used to from a textbook. So it's the same thing. So that's what we're going to do right now. How do we do that? Similar to getting the potential function for a 2D vector field, except we're going to have 3 integrals to evaluate. We're going to do m dx, followed by n dy, followed by the p dz's integral. And then we're going to add all 3 together, except we're going to only take one instance of any duplicates that we see happening, because you don't want to add any duplicates together. Okay, so what is the integral of y squared cosine x, but with respect to x?
I squared sine x.
Now, now watch out here, because I'm going to get a little strict about this. Don't put plus h of y, because we're now in the 3D world. We're in space, vector field in space. You don't put just, a function of y. Because we're integrating only with respect to x here, and we're not doing y and z's, your function here, I'll call it h, is a function of 2 variables. So parentheses y comma z. That's how we indicate it's a function of 2 variables, y's and z's. And it might be just a constant, but we don't know. And you have to acknowledge that fact. Okay, then the next integral, you're going to integrate, 2y sine of x plus e to the 2z power, but with respect to y. Okay, I think I'm going to get, for the first term, y squared sine x And for the next term, the e to the 2z with respect to y, I think that's going to be y e to the 2z. And then plus extra junk g, which is going to be a function of two variables, the other variables that we didn't integrate with respect to at this moment, which happen to be x and z. And then last, but not least, we're going to integrate that last component, 2y e to the 2z power, with respect to z. And that's just going to end up being y e to the 2z, and then you're going to acknowledge the other two variables, f of x, y. I hope you see that, we have duplicates here. We got a couple duplicates of these other guys here. Please don't add those together. The potential function for this vector field would be y squared sine x plus y e to the 2z power plus c. And that's it. Now, we're going to use that to help us evaluate the line integral. So this line integral, the FDR line integral with the starting and stopping points glued onto the integral on the top and the bottom, that's giving us the starting and stopping points for the path. You're going to take this y squared sine x plus y e to the 2z power and evaluate him between starting and stopping points. And as usual, always plug in the upper limit first. So if you plug in pi halves 1, 1, you have 1 sine of pi halves plus 1 e to the 2 times 1 power minus, and then substitute the beginning point. So you'll have negative 1 squared sine of 0 plus negative 1 e to the 0. And then sine of pi halves is a nice number. It's 1. So you're going to 1 plus e squared, okay, minus 0 minus 1, I think, like that. And then when you distribute this minus, you get a minus minus 1. That's 1. So you have 1 plus e squared plus 1. And I get 2 plus e squared. And voila, that is the final result for our line integral. Questions?
I'm good.
Okay. So check out example 6, and I put this in here because there's going to be one similar to it on your quiz on Sunday and Monday. So watch close for what's the different flavor. So first they want us to prove that differential form is exact, and that just means prove that it's a conservative vector field, and it's going to end up being exact, but you got to prove it first. Then we're going to use the fundamental theorem of line integrals. And here's what's weird. This curve is piecewise smooth. It's going to start at 1, negative 1, 2. It's going to go to 3, 4, 5. And then from the 3, 4, 5, it's going to end up at 1, 4, 3. Do we need to do two separate line integrals? In other words, should we do a line integral from the negative 1, 2 to the 3, 4, 5, and then add that to the result of the 3, 4, 5 to the finishing point, 1, 4, 3? And, and then sum the results? Or should we just do one big ass line integral where we ignore the middle point, that 3, 4, 5, like, screw him, he's just like a layover. Have you ever been on a trip where you have a layover in some weird city that you don't care about? You're like, I hate when that happens. Like, if you're flying to New York, sometimes they make you stop over in Chicago for like 5 hours. You're like, oh man, I didn't want to go to Chicago. You're sitting in the airport eating airport food. Really sucks. So which should I do?
I'll go with the big one.
Good. We are only going with the big one. Now, folks, for those of you who like lots of work, you're like, hey, I love pain. Give it to me. Well, then go ahead. Do the first line integral and then add that to the second line integral and sum the results, then you'll get the answer. But that's a lot more work than, just ignoring the middle point. You can ignore the stopover. When you go on a journey, don't you only care about the beginning and the ending points? Yeah, same thing with line integrals. You don't care about any intermediate stops along the way. You still only care about the beginning and ending point. Isn't that lovely?
Yes.
You're
Very
supposed to
lovely.
say, thank you for saving me a lot of work. Because I'll get students, I'll send them on a wild goose chase. Like, oh, we start here at this point, then we go to another 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 point, and we finally end up at our journey. And they end up doing all these little intermediate line integrals, wasting lots of time, and then adding the results. And they get the right answer. Sure, they get the right answer, but they could have just done a straight shot. Who cares about those intermediate stops? This is independent of path if your vector field is conservative. And you only care about the beginning and ending points, and that's it. So remember that. Save yourself time. Save yourself work.
Well,
Okay.
That's only if it's conservative.
It's only if it's conservative. If it's not conservative, oh boy, yeah, you're going to have to do, if you have like 56 intermediate stops, you're going to have to do 56 intermediate line integrals. Congratulations. Ugh. I'm never going to give you anything like that, but I'm just saying it wouldn't be in a path. You'd have to do every intermediate step. Okay. So first, let's prove it's exact. So how do we do that? We need to show that f is conservative, and that will prove that the differential form is exact. So we have our m, you cherry pick it right off of there. You have your n and you have your p. And so if you're going to do the theorem to test for a 3D conservative vector field, first, you have to do is dm dy equal to dn dx. So dm dy, the derivative of 2xyz with respect to y is 2xz. And that happens to equal dn dx, because the derivative of x squared z with respect to x is in fact 2xz. So there's one. And then you're like, okay, what else? Well, take a look at p and take the partial of p, which is x squared y, with respect to, what am I doing here? There's example 6. Okay, sorry. Which the derivative of x squared y with respect to x is 2x,
2.
xy. Is that really equal to what it's supposed to be equal to, which is dn dz?
Yes.
Hang on a minute. We got, I'm
X
sorry.
squared.
This is dm dz. Sorry. I'm writing it down wrong. My bad. It's going to be dm dz. So if you look at m, the derivative of 2xyz with respect to z is in fact 2xy. So those are good. And then the last check is, this is when you look at dp dy. So the partial of p with respect to y would be just x squared. And is that equal to, you hope it's equal to, dn dz? And it is. So you're like, yay, it's conservative. Great. So that means that the differential form is exact. That's what you just proved. Now what? Use the fundamental theorem of line integrals and evaluate the line integral. Okay. Well, they didn't give us a line integral. Yeah, they did. And they give you a starting point and an ending point, and you don't care about the intermediate point. So if we get the potential function by integrating 3 separate times, you're going to integrate 2xyz with respect to x. I get x squared yz plus some function, and you're acknowledging the 2 other variables that you didn't integrate with respect to at this moment, which is y's and z's. When you integrate n, which is x squared z, and integrate him with respect to y, I also get x squared yz. Hey, that's a duplicate. Plus g, which is a function of the other variables we didn't integrate with respect to. That'd be x and z. Finally, integrate x squared y with respect to z. Oh my gosh, I still get x squared yz again. My God, I got 3 times. Is that legal? Yeah. Do you add them all together? No, 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 no. So your potential function using everything that we just did here is simply going to be x squared yz plus some constant. And so then the line integral, and I'll just write line integral, is equal to x squared yz, and you're going to evaluate it between the beginning point, which is 1, -1, 2, and you don't care about the intermediate point, like ignore that. Just look at the finishing point, which is 1, 4, 3, And then if you just plug stuff in here, I'm going to have 1 squared times 4 times 3 minus 1 squared times -1 times 2. And I think what we have 12 minus a minus 2, I get 14. And we're done. Oops, that's 14 is your final answer to the line integral. Okay, questions?
What was it that we did there? Was that like the island hopping you showed there, or
No, that wasn't island hopping because otherwise we couldn't even apply the theorem. That's just you have some region here. The region has to be simply connected, and within the region, you're just going in between points.
oh, I see. Okay.
It has to stay in your region. Like if your region is Hawaii and you have to actually leave the region in order to do your stopovers, you're not even allowed to apply the fundamental theorem. It has to be, nice.
Okay,
That's
thank you.
all. You're welcome. Okay, you guys ready to try one?
Let's do it.
Okay, now I want to just warn you that this is a little tricky in that they're not giving you the vector field. Okay, so you and a buddy are going to do this, but I want you to notice they did not give you the vector field. Does everybody see that there's no vector field? Let's just look it over. It's multiple choice. Hey, cool, multiple choice. So they're telling you a scalar function here, and yet they want you to do this line integral. And the curve is some smooth curve between, a starting point and a stopping point. So I'm going to let you and the buddy argue about if there even is a vector field involved here, and I claim there is. But they're giving it to you in a weird way. So talk about that and be ready to, discuss that in a little bit more detail when we come back. Okay. So I'm going to throw you in with a buddy right now. And when your room opens up, I'll see you in a bit. Good luck. Have fun. Multiple choice, baby. Enjoy. So Emily, you are correct in pointing out that this is already the potential function. Woohoo! So you didn't even have to do any work to recover this potential function like we've been doing the last few examples. Pretty good, huh? You don't have to do any integration, nothing. So where's the vector field?
The gradient.
Partials of the functions or the function.
Look at this right here, people. Eyeballs right there. You guys recognize the gradient? Hello?
Yeah.
The gradient of f is a vector field, right? That contains the partials of the potential function. Hello?
Yeah.
Correct.
Yes.
So a vector field actually is involved in this whole situation. It's the gradient. And the gradient is understood. Gradients are always conservative. Why? Because they've got potential functions that they come from. So you don't even have to go prove independence of path or the vector field's conservative or la that we've been doing the last half an hour, because it's understood. Gradients are already conservative vector fields. Nice. And you're given the potential function. Nice. So what's the only thing you had to do in this whole problem to give the result of this line integral?
Show that it's conservative.
You don't have to show it's conservative. No, really, you wasted valuable time. It's under, let me repeat what I just said, because I think you guys are tired. When you have a gradient, gradients are automatically conservative. Please don't ever prove to me that a gradient is a conservative vector field, because I will go, thanks for the point, thanks for the tip, but you're already guaranteed that a gradient is a conservative vector field. End of story.
Oh my goodness.
Period.
Wow.
Done. Like, unless you like pain, like, oh, let's do some extra work just because I like doing extra stuff. Hey, knock yourself out. But you don't need to, because gradients are by definition conservative because they have potential functions to them. That's where you got the gradient from. Does this make sense, people? Is anybody listening?
Yes.
Hello?
Yeah.
Hello? Wake up! Wawooga! Wawooga! Yeah, no work needed. All you needed to do was, oh God, they gave me the potential function. How easy can this be? And if I put something this easy on an exam or a quiz, and I'm going to, and you waste valuable time by going off, on some wild goose chase to prove it's conservative or beep, bop, beep, beep, please don't bother. Just take the potential function that they gave you. They gave it to you on a silver platter, and they gave you the starting and stopping points. Yay! And so all you had to do this problem was do a whole bunch of substituting. Oh my gosh, it was that easy. Yeah, sorry if I made you think there was a lot more to it, but that was my point. That was my whole point. So hopefully all you did was this, and then you did a little bit of arithmetic. And I think I got 81 minus 4. And I think the final answer was 77. And I think that is one of the choices. Woohoo! Yeah? Oh, bummer. So it looks like, can you guys hold on a second while I forgot to do something really quick. Oh, I'm so mad at myself. Mhm. Oh, no, I didn't want to do that. Okay. So no, let me get out of here. I need to, oh, I know what I need to do. Yeah, it's probably over. Never mind. I know where it is. I need to go grab it somewhere else. I changed your course reader behind your back while you weren't looking. What? Yeah, you already have a course reader that's obsolete. Really? Yeah, come back next semester and take me again. I'm being a little facetious right now, people. But what I did over the weekend is I added a problem to this lecture that's not in your course reader now. And so the students next semester will get to have this in their course reader. Well, that's not fair. No, I'm giving it to you now. And I'm mostly doing this for George because, oh, it's not even here. Yeah, I'm going to have to bomb out. Let me, yeah, I am mad at myself. Ooh, how do I exit out of here? Oh, that's how I get out. Okay, hang on. Okay. Wow, this computer is so slow. It's so annoying. I can't even believe it. Okay. So what I'm going to do here is I need to put something on my flash drive here real quick because I guess I didn't put it in there when I updated over the weekend, which so I'm still here. Don't move. Don't go anywhere. Let me see if I can do this. Just double check that I did update it. No, that's not it. Huh. I may have put it in a different location. Let's just see if I did. No, I thought I did. Wow, that's really unfortunate. I hate it when I do that to myself. I think I do some work and then I didn't really do it. Oh. Okay, let's see if it's here. Wow, this is so annoying. Nope. Where is it? Yeah, this is it. Nope, I didn't put it in there. Well, Boy, am I having to do this all over again. I hate it when I have to do work all over again. All right, so I screwed up. So let's, sorry. I don't know where this went. Missing files. Don't know where my files went. I thought I spent a whole weekend doing stuff, and I guess I wasted my whole weekend. Cool. Back to where we were. Apologize for that little side trip there. Just when you think that you're trying to do good, you didn't do good because you didn't save your file. I don't know what happened to my file. So I'll just put the problem on here. So George, this is actually a problem for you. But anybody who's taken differential equations will recognize it as well. Wow, my computer is so slow. It's hellacious. Come on, baby, you can do it. Okay, so I'm just going to have to put this problem in here and make a note to myself that I have to update this file again. I don't know where it went. That's really unfortunate. Okay. So let me append a page here. So George, you asked me a while back, and you seemed really exasperated when you asked me. So I just want to say I kind of recognized your disappointment when you asked me this question. Yeah, Nick, exactly. So the thing is, George, that you were upset because you said, you know, hey, 1 apple plus 1 apple is equal to 2 apples. And you seem pretty upset that that isn't the case when I taught you this shortcut version of finding the potential function. And you're like, and I said, my answer to you is probably not the type of answer you wanted, because I just said, accept it, essentially. So this problem, I stole this problem from a colleague of mine who teaches differential equations, but he gave this problem on an exam, but in the context of differential equations and exact differential equations. But I thought it was so cool that I stole it and made it part of my lecture, although apparently I did not, because I didn't save my file. I'm going to have to write it up all over again, I guess. So the question is, if you're given, please God, can I have one break today at all? One break is all I ask for, God, please. So the instructions are, if possible, George, find a function n. So n is not given, okay, George? Everybody listen up, because I may put this on an extra credit. Oh, yeah. That will make the line integral exact. And I'm sorry I can't write fast enough. So mad at myself. If it's not possible, just say so. Okay? So you know how I'm pretty anal about asking you folks to always put like plus h of y or plus the extra, and I'm telling you right now, I'm going to dock you points if you don't put it on there. Okay? And like if you're trying to find the potential function, this last one you were given the potential function, so you didn't have to. But see how in this problem here you find the potential function. Sorry. And you had to integrate, say, 3 times, and I had you do 3 of these puppies, H, Y, Z, G, X, Y, F, X, Y. If you don't put those on, -3 points. You got to, because you have to acknowledge what you aren't doing. So this problem basically requires you to acknowledge that. So they're giving you M, and they're not giving you N, and they're going, hey, make this exact. Now, this is different from a DE problem, because DE, I know some of you are going, oh, I know how to make it exact. No, you don't, because they're not giving you N. You're thinking of finding an integrating factor. That's a different conversation. So what you're going to have to do is you're going to have to integrate the M, with respect to x, and that's not going to be too easy because this is kind of a hard problem. Oh, by the way, that was supposed to be y to the positive half. I just copied it down wrong. And you're going to integrate that with respect to x. Okay? So you're like, well, I thought they're trying to ask us to find n. Stay with me on this. Okay? Stay with me. Because if you understood that last problem about the gradient and all that good stuff, then you'll understand this. Okay? So first, how do you integrate x to the minus a half, y to the half, but with respect to x? Well, you know, you're going to use the power rule, and so you're really going to integrate the x to the minus a half as 2x to the half, and then multiple y to the half. Here, you're going to use the log rule, and I always like you to tell me your u and your du, otherwise I dock you points. So I need a 2, so, you know, I'll have to put in a, when I'm integrating this, I'll put in a half, and this ends up being a half ln x squared plus y squared. Plus extra junk, not just plus c, but plus h of y. Now, we don't have n because we don't know what n is. It's like, well, you know, crap. So what can we say right now? What we can say is that n, you know, if this were the potential function, you know, because it has extra junk, let's just put f of xy, because it could represent the potential function here. Then n is supposed to be the partial of the potential function with respect to y. So then you're going to basically take the partial with respect to y of this entire expression. Sorry. And this is why you have to have the h of y, George. Okay? And you're like, who cares about that? And who cares about all these like duplicates and all this other stuff? Because you need your n to be the partial with respect to y of your potential function. And so when you take the partial of this, and this is not too hard with respect to y, oh, so you're going to have to take this guy's derivative. And then the partial, and this was one of the quiz problems, you know, how do you take a derivative of a logarithm? You know, the 2 stays there, you have x squared plus y squared. Is that supposed to be x squared plus y? That's x squared plus y. Sorry, that was x squared plus, did I have that? That's okay. And then I think that's going to be, what's the derivative of y squared with respect to y? 2y, these 2's cancel, plus h prime of y. And there's your, and then you can clean this up. But there's your answer. So your n is going to need your h prime of y in there as your answer. And if it's not, you blew it. And also, if you had added 2 duplicates together, what happens is you won't get like your correct result. Like you'll get something else, okay? So here you didn't have the duplicates because you didn't integrate twice, but what would happen when if you add your duplicates, you'll end up with not a conservative vector field, okay? So I just thought this was kind of a cool beans problem, mainly because for those of you who you haven't maybe experienced it yet, but you're gonna, I'll be taking points off your quiz. Even if my math lab gave you full dish, if I don't see the h of y's or the f of x's or any of that other stuff, okay? You need to put it on there. Okay, so gotta leave a note to myself. This up. And let's do equivalent conditions. So to wrap this up, say you've got a line integral that's independent of path. Let's say you started at 0, 0, you went to some intermediate point 2, 1, and then 2, 1 back to the point 0, 0. So you basically finish where you started. What do you think the line integral would be? What would the line integral result be?
0.
0. Very good. Yeah, because you're starting and stopping at the same point. So, you know, was there any work done? No. So now let's do a definition and then we'll do the equivalent conditions. We say that a curve C is closed if the starting point, the vector valued function evaluated at a seconds, is exactly the same as the vector valued function valued at b seconds. It's closed. And that just means it has the same starting and stopping point. So the 3 equivalent conditions are, and when I say equivalent conditions, if one of them is true, you automatically get the other 2 for free to be true. So if you've got a vector field Mn and P, and this is also good for two-dimensional vector fields as well, it's all good. You got your partial derivatives are all continuous on some open connected region R. Let C be a piecewise smooth curve. The following three are equivalent. Again, if one is true, the other two you get for free. They're automatically true. So one statement here, if you're saying F is conservative, then that also definitely means that the vector field is somebody's gradient for some potential function F. Okay, if that's true, then number 2 is automatically true. This line integral here, FDR, is independent of path. And we already saw that theorem. And then if that's true, then this is true. Your line integral will equal 0 for every closed curve, C in R. Now let's do some notation. The notation for a closed curve line integral, like you'll know the curve is closed, if they put a little, you notice on this line integral symbol, they have a circle right around the middle of the integral symbol, just a little circle right there. That means it's closed. The curve is closed. Just means the starting and stopping points are the same. So that is kind of nice to know. So now let's do some equivalent conditions theorem applications. So check out this line integral here. Let's say you started at the point 0, 0, and then you went to the point 4, 1 like that. So we'll call that curve C1. And then from the point 4, 1, you went to the point 2, 3. So you went over here, a straight shot, say that's C2. And then from there, you went all the way back to where you started. Boom, right there. What would the line integral value be? Well, I want you to notice that dm dy is equal to -3. And notice they're trying to trick you there. See, there's a minus sign right there. What should you do, differential equations people? You should know this because you may have been tricked on a differential equations quiz. I always try to trick my DE students. You better change that to plus a negative and then distribute the negative because your n always has to be sitting next to a plus sign. So your dn dx is also equal to -3. So we have a conservative vector field, which means it's independent of path, which means all these equivalent conditions are true. So can you see that this curve here is closed? We go around this triangle, we
Yes.
start to stop at the same place. Then that means the line integral is equal to 0, and I'm done. Similarly, let's say you started at the point 0, 1, and you went down to the point 0, -1, okay, right there. And then you went along the graph of x equals, oops, that's not right. X equals, this is the semicircle here. And you went right back to where you started from. So you get back to the point 0, 1. Hey, closed curve. So again, don't bother doing any work. Closed curve, line integral equals 0 since it's a closed curve. You start and stop at the same place. Don't bother doing any work. So let that be a lesson to you. If somebody says, hey, I want you to go do this line integral and it's a closed curve and it's conservative vector field, heck, don't do any work, say 0. Okay, and you're done. And so my final meme of the day is every time you compute the line integral for a conservative vector field without using the potential function, you kill an adorable math puppy. And how dare you? Would you even want to do that? I hope not. Okay, and that concludes today's lecture. Thanks for putting up with a running around, but we got everything together here. Okay, I'll stay for 5